Welcome to the next vlog. Today I'm going to have a quick discussion about something that came up recently and a claim. I'm just going to refer to it as the magic wand. It's his Flux detection system. Now, we've been looking at these for many years. In academia and stuff like that, usually these systems work great in a lab where you have an isolated system, often a device in a Faraday cage, so outside interference isn't coming in, and you place the transducer either as an antenna in there or whatever else. So we're going to use an antenna approach. The system I'm going to use is a little different. It is this little device here, which is part of a circuit we're working on for partial discharge detection in low voltage machines. Again, a wand, but a different type of wand where we're looking at megahertz and potentially gigahertz, and then doing some stuff in order to create a sniffer of some type. And I'll show you that on an oscilloscope. We did use this with it, but the low end of that is a little on the high side. But it'll give you an idea of what can be seen across certain systems in a lab environment. And then once we're done with that, I'm going to show you what happens in real life when one of these systems has been deployed. We were called in to take a look because a company had spent a lot of money over and over again repairing a condition that didn't exist. Well, did exist, but not on the system they were looking at. What most people don't understand is that these things are supposed to detect some, the fringing or a little bit of flux that's part of the losses of the machine that's so small that if it's near a fluorescent light, that fluorescent light can overwhelm it. We did an RF meter test to show that radio frequencies in the line frequency range of the machine were being overwhelmed by overhead lighting in the lab type thing, so we didn't use a Faraday cage. Which also brings up another thing. Every machine frame is different and basically becomes a cage. So even when we're looking at this partial discharge ability, we're not looking for something that's going to give us an exact value as a sniffer. We're looking for something that's going to give us an idea if it exists, because the frame of the electric machine becomes an antenna. And I'll get into that a little bit later. So let's go play in the lab. So here's the setup. I have a little, I think this cost me about $8, a little RF receiver. We have this set up here, and little antenna. This is actually just a cell modem antenna set up next to the motor. So what we're going to look at is the emissions from this in this condition where basically nothing's set right in the drive deliberately. Okay, so right now you can see I'm showing nothing here. Okay, you can see that just kind of wobble a bit. Now it is energized, but that other ripple you're seeing, that is the lighting system and other electronics going on here. So let's go ahead and we're going to select run. Let's go ahead and watch. And you can see that, it picks something up right away. A little chaotic and stuff, but it's there. Okay, whoop. Should have probably done this on the screen instead of with the camera. So I'm running at about 50 hertz. And you see some stuff coming in and out of phase. Now this is very interesting because it's on a lab table. But what happens when I start adding in other components in the area? Like turning on my cell phone, which was part of the other thing. Anything else that puts out an RF frequency and of course the skin on the motor itself. So this is where the concept comes about that the magic wands will work. So let's go ahead, and what I'm going to do is I'm just going to move this wand around different spots related to the machine. Let's go over here, there. Now we're close to the drive into the machine again. Now let's take it a little further away. You can see it's emitting everywhere. So let's go ahead and we're going to get back to our discussion. But in the next week or so, I'm going to use this little $10 device or under $10 device, and we're going to connect it up to an Empower input and see what it looks like. So the particular location I was talking about, where we were called in, had been using a combined system that included a one of these probes, and they had just finished spending several $100,000 trying to correct a critical piece of equipment. So we were asked to come in. Now, one of these companies has suggested, by the way, which tells me immediately they have no clue as to what current or electrical signature analysis is or its capability, suggested that you can't get speed out of current or electrical signature analysis. Well, again, I call that marketing science because it's not real science, in which both 40 years of field experience tells us the exact opposite. Field and laboratory and everything else. Matter of fact, very precise speed measurements down to the hundredth, in some cases, thousandths of an RPM automatically. So where they come up with that? Well, it's strictly their investment-owned company. They're trying to make money by lying. And I'm not going to hold back on that because I have no problem with the truth. So let's talk about one of these magic wands in application. So we do, and I'll put some other stuff up, and I'm going to continue this over time because I receive in my position reviewing papers, studies all the time where, actual engineering studies like university and real companies, that have been playing around with these things. And they go out and they go, oh, okay, in the lab it worked like this. Oh my gosh, we put it in the field and all this different noise. Well, this was a case of all this different noise. So we went in because they were saying that they had a 250 horsepower motor that had all these problems. Now, we looked at it and identified some misalignment. We confirmed that with motion amplification and some greasing. Okay, so this was a cage-related issue. This is the actual electrical signature data. And accurate running speed. Ha ha ha. Because it's easy. And this was even while the machine was on a variable load, a one-off test. This is not machine learning, folks. So we took a look at that. We then went ahead and started taking a look at what was actually going on. And so we did another FFT, and this is what they were claiming was wrong with the particular piece of equipment. So they were calling this, whichever direction I have it on the screen, but they were claiming this was the electric motor itself. And you can see an oscillation saying there's a rotor problem. 250 horsepower motor is not a cheap replacement. Multiple times, having to look at structural analysis and everything else because they were also calling out severe unbalance. Now, what was interesting was we had them vary the speed and everything else on this electric machine, and this stayed rock steady. So even when it was operating at 45 hertz, they were calling out the same numbers and everything else because da-da, they were how these things work is they're supposed to pick up on the stray flux, which is an extremely tiny value, so little that in a large electric motor an LED light in the area is going to cause it to kind of do whatever. But when you have a bad ground and you're inducing stuff into the ground for all of the machines, in this case, an 1800 RPM machine in another part of the building, but the drive was in the same motor control center, was inducing, because it wasn't set up right, inducing this ground. You'll notice that it's not a lot of current. Well, they weren't worrying about the actual current. They were looking at the magnetic field, which I'm trying to comprehend how they're relating that to energy losses. But, you know, I'm not even going to go down that road. It was such a joke. But in any case, so I get this oscillation. That looks everything like a pole pass frequency in a bad rotor. So they were replacing these motors on continuously because, yes, a particular brand of motor is known to have casting voids. This one had a small one, but really, let's go to the actual thing under load. Small peaks, but really nothing like what the claim was. Heaven forbid we should get actual speed. In this case, we were even able to identify. So we were running at 1789 RPM, 0.2 RPM on the one machine. We were looking at this. This is telling me, say, 1789.5 RPM, which is how we matched it to the other motor with a device that these yahoos claim can't tell running speed. So if they've even claimed to somehow be working with me on crap at one conference. You know what? No, that ain't gonna happen. Sorry, folks. I deal with a lot of companies, including a lot of competitors, in real professional environments, like where we write the standards for this stuff. And I have a thing about, this. So this is what they were detecting. This is because the current goes into the frame of the machine, which, by the way, acts as a Faraday cage. Or a partial Faraday cage, which reduces that flux even more. Because if these magic wands were to actually work, whenever you walk by an electric machine, your hotel key or your credit cards would magically erase. But that's neither here nor there. They don't. You aim all the field into the thing. You get some fringing, which is that flux. It would take a catastrophic failure of a machine to get everything out that they claim, unless I'm in a laboratory environment or I'm in a Faraday cage, and I'm looking at the very small values in a laboratory, in special conditions. But when I go out in the field, I don't see those special conditions anymore. So let's take a look at a couple of more things, and then we'll conclude. This one is an RF meter, which basically, this looks in the 60 hertz range, so the scan rate has it bouncing around, but you get an idea that there's something there. Now, this is really important because of what we're going to show next. But in any case, let's see what happens as this shuts down. Okay, not a significant difference. Drive shuts down. And you saw it jumped up there. Well, what is all that other noise? Well, that is things like my lighting and other conditions in the area. So let's go ahead and we're going to stop here and move on to the next. So in this case, this is a flux meter. So we are actually going to be taking a look at the level of flux in the area. So right now you can see I am at a specific value. That's the temperature in here in degrees centigrade. Let's take a look over here. Now everything is off. Let's go ahead and turn it on. Values still haven't changed. Okay, let's go ahead and start the machine up. There we go, we're starting to see some. Yoo-hoo! Something's happening. Values are very low. They're actually lower than the outside. Okay. Oh, let's see over here. Yeah, here, 2.6. Okay, let's go ahead and I'm going to just set this near the front. Now, what's important to understand, you see the bubble on there? There's actually a scale underneath that plastic. That's because when you set something up, it's got to be the same no matter what you do. So we're going to go ahead and I'm going to set this in a position here. So we're getting this end flux. All right, let's see if it changes at all if I go this way. 0.3, okay. We have to be very careful. Say I'm doing the flux in a field in an exposed electric DC machine. So here we go, now it's settled. If I wave my hand around, I can affect it a little bit. Let's see what happens as we shut down. Okay, so 2.6 Gauss, no change, 0, 2.6, 0. Not still flashing back and forth. Let's see what happens when I hit this. Huh, so 2.6 must kind of be the Gauss in the air. Yes, it is. And depending on where I position it in the area, there it is. So that is remaining field from when I ran the machine last. Let's go ahead here and turn it off completely. I'm still 2.6 to 2.8. You saw there's a lot of things that affect what we're looking at. Now, this is not the end of this. We're going to continue. I've got some toys on the way, so in a few weeks we're going to really get into it, both in the lab and possibly even in the field. So we will see what happens. In the meantime, we'll also show some experiments as we move forward with the little wand that we're working on for detecting PD in low voltage electric machines. But that about covers it. You've seen the videos we've been doing on electrical signature and current signature analysis, so you're aware that there's the ability to detect speed rather accurately. So please feel free, keep making me aware when some of these companies make these claims. I'm got no problem proving or disproving them. Right now, I tell you, I've been, disappointed. So with that, have a great day, have a great weekend, and we'll see you next week when we have more fun.